what, 36 hours or so. It feels like more than that. But welcome today. There will those of you we're going to have pizza showing up at some point. What we'll do is after the talk, then we can have pizza rather than before the talk. So there will be pizza here afterwards as well. So we can have a little bit of an opportunity to talk with Nicola afterwards as well. So I'm very pleased today to introduce Nicola Maher. Nicola is visiting us from CIRES in Colorado, where she holds a CIRES postdoctoral fellowship with Jen Kay and Antonietta Capotondi at the NOAA Physical Sciences Division. Prior to showing up in Colorado, Nicola had a Alexander von Humboldt postdoctoral fellowship at the Max Planck Institute for Meteorology, where she led the large ensemble, the Max Planck Large Ensemble project there. She has a long history of interesting research in tropical variability, Enso Variability, Decadal Variability. She did her PhD at University of New South Wales with Matthew England and Alex Sengupta, looking at natural drivers of decadal variability in the Pacific. And that PhD thesis won the best PhD in Australia for meteorology, oceanography, geosciences, glaciology, and climate. So quite an award. We'll be talking today about some of her work using large ensembles to look at Enso variability. It's been really nice having you here. We've enjoyed your trip, and she's also she's done with her position in March this year, where she's going to spend 2 months rock climbing through the southwestern U.S. before she goes back and starts a faculty position at Australian National University in oceanography, climatology, just the geoscience department. What's the department?
Climate and ocean.
Climate and ocean department.
I think it's climate and ocean physics.
Okay. Wonderful. So welcome. It's been very nice having you here.
Thank you.
Look forward to speaking.
Thanks for the introduction, and thanks for inviting me to come and talk today. If I don't have a microphone, so if you're at the back and you can't hear me, just like wave your arms and I'll talk louder. So yeah, today I'm going to talk a little bit about some work I've done over the past 2 years as a postdoc at CIRES and CU Boulder, and I'd like to acknowledge my long list of collaborators who all contributed to the work I'm going to show today. Okay, so today I'm going to try and address 2 scientific questions, and those are using single model initial condition large ensembles that we like to call SMILES, to look at the combination of Pacific decadal variability and ENSO in driving the temperature and precipitation we see over North America, and to look at future changes in ENSO itself. But before I realize that I've thrown up a whole lot of acronyms already on my first slide, so I'm going to take a little bit of time to step back and go through what I mean by all these acronyms and why they're important before I delve into the scientific questions. Okay, so let's take a big step backwards and talk a little bit about ENSO. ENSO is the El Niño Southern Oscillation, and you can see a fun Australia-centered schematic here because you can tell by my accent I come from Australia. And the El Niño Southern Oscillation is an interannual mode of variability, so you can see it on kind of 2 to 5 year timescales that really occurs in the tropical Pacific. And we care about it because it has impacts all around the world. And so here you can see the 3 states of ENSO. We can have the neutral or the normal phase of the tropical Pacific, shown up here on the left. And here what we usually have are trade winds that blow from the east over here to the west over here. This pulls up kind of warmer water in the west and allows cold water to upwell in the east. And where I come from, that means we kind of get average rainfall over Australia, but it also does things like allows for good fisheries off the South American coastline because you have this cold, nutrient-dense water coming up on the coast. When we have an El Nino, those trade winds weaken, and this tends to give us warmer anomalies in the eastern Pacific than we're used to. And it messes with the rainfall, as you can see in this schematic on the bottom left. And so in Australia, that means we often have droughts and bushfires, but it also has impacts in North America and all around the world. And then our last state is the La Nina on the bottom right, and that's kind of the opposite. Our trade winds intensify, and this kind of intensifies everything I talked about in the top left neutral panel. So, more trade winds, this gives us kind of colder anomalies across the tropical Pacific, and increased convection over kind of Indonesia and Australia. But ENSO has impacts not just in Australia, but also in North America. And you can see some of these in the schematics on this slide. So you've got a typical El Nino winter on the left and a typical La Nina winter on the right. And you can see that this induces different anomalies in different parts of North America. Some places are wetter, some places are drier, some places are warmer and colder. So ENSO really matters for trying to understand, I guess, how much rainfall and what kind of temperature anomalies we have in a given year. I also mentioned something called Pacific Decadal Variability or Pacific Decadal Oscillation. And here I'm talking about another mode of climate variability that occurs in the Pacific, but this is more kind of centered in the North Pacific. And today I'm going to characterize all Pacific Decadal Variability by just looking at the PDO, or the Pacific Decadal Oscillation. Here you can see that pattern associated with the PDO on the left. And really what we see is this kind of typical kind of pattern in the North Pacific where you have these kind of warm sea surface temperature anomalies off the coastline of North America, and you have this kind of cold blob in the central North Pacific, and you have a typical kind of circulation that occurs in the atmosphere. If you look on the right, you can see the PDO in a whole bunch of different observational products. And what you can see is this is really a decadal oscillation. So you're seeing kind of 10-year periods where the PDO is positive or negative. So it doesn't really occur year to year, but it kind of occurs decade to decade. Okay. The PDO also has impacts all around the globe. Here is a plot taken that shows temperature impacts on the top and precipitation impacts on the bottom. And you can see in different parts of the world you get kind of different impacts based on this decadal oscillation in the North Pacific. Okay. And so one of the questions I'm going to address today is looking at how those two modes of variability, ENSO and the PDO, combine to impact North America. And they both have impacts on North America, as shown in this plot here. So you've got rainfall or precipitation on the left, temperature on the right, PDO at the top, ENSO at the bottom. And the first thing you'll kind of note is, well, they have kind of similar impacts on North America. The overall patterns look pretty similar for the two modes of variability. However, there are regions where the differences matter. For example, if we look at precipitation on the left, you can see that ENSO has a way stronger impact in the center US than the PDO. And if you look over there to the right, you can see that the PDO has stronger temperature impacts on the western coastline than ENSO does. So similar impacts kind of over the continent, but regionally a little bit different. And so previous studies have tried to look at how these two modes of variability combined to drive temperature and precipitation in North America. And this is one of the kind of original studies that did this with observations, looking at El Niños that occur when the PDO is warm on the left and El Niños that occur when the PDO is cold on the right. And here kind of dark colours are one extreme and light colours are another extreme, and this study originally concluded that there are differences. But the problem with studies like this are the PDO is a decadal mode of variability, and we don't really have that many observations, so we don't have a lot of sample sizes. So trying to understand statistically significant differences between the two in observations can be a little bit complicated. Okay, and so because of that, today I'm going to use these SMILES, or these large ensembles, to revisit the combination of ENSO teleconnections and PDO teleconnections, or PDO and ENSO impacts over North America. And I'm going to do that in multiple SMILES, or multiple different models, to see if our results are consistent across different climate models. And so you might now be asking, well, she's mentioned this large ensemble smile thing a whole bunch of times. What is that? Okay, so a smile, again, is a single model initial condition large ensemble, which maybe tells you something, maybe not. And what you can see here is a time series from a global climate model. It doesn't have a y-axis, but it should, but this is global mean surface temperature. So this is the temperature of the Earth over time in a single run of a climate model. And so you can see temperature kind of wiggles over time. This is known as climate variability. This is the fact that the Earth is chaotic and the climate from year to year is a little bit different because there's chaos in the system. But if you look at the end around 2000, you can see it's a bit warmer than the beginning if you kind of take an average. So that's global warming. And so when we run a smile, what we do is we slightly perturb the initial condition and we run the model again. So we run it exactly the same way with the same external forcing, the same volcanoes, the same solar radiation, the same greenhouse gases, and we get another realization. And that's the blue one. And so you can see it again, it wiggles, it has this chaotic variability, but again, the end is kind of warmer than the beginning with the global warming signal. And when we run a smile, we do this a whole bunch of times. Modeling groups usually do it between 20 and 100 times. And so we can keep adding lines. Again, and a whole bunch. And this is actually 100 lines. This is the largest of the ensembles. And so here you can see what I was talking about. All of the lines kind of wiggle due to variability, and we can really capture how large that variability is in the climate system by looking at the spread of these kind of pale blue lines. You can see that the end is warmer than the beginning, that's global warming again, and we can see some kind of interesting features. If you look at 1991, way over there, you can see that all of the ensembles kind of drop in temperature. And that's because of Pinatubo, the volcano that chucked a whole bunch of aerosols in the atmosphere and cooled the globe. Okay. And so the advantage of smiles for the research question I'm going to start with is that there's lots and lots of events. We've got all of these simulations of the world we live in today, and we can start to composite years where we have an El Nino and a positive PDO, or El Nino and a negative PDO, or La Nina and a negative PDO, and start to see if there are statistically significant differences. And I mentioned I'm going to look at multiple models to check the robustness because we know the models can represent the real world, but they're not perfect. Okay, and so that brings me back to my first research question, which is, does the Pacific Decadal Oscillation modulate ENSO teleconnections over North America? And so before we try and answer this question, the first thing we really need to do is say, well, do these models actually represent ENSO teleconnections? We do have some observations. Do our observations and our model look similar? Okay, and so we can do that here. So here I'm showing ENSO teleconnections, or ENSO impacts over North America. Red and blue are temperature, green and brown are precipitation. The top left of both is observations, and then every other panel is one of my smiles. And here I'm showing the member from the smile that has the highest correlation with temperature observations. And you can see those correlations in the top for temperature. And so you can see that we have pretty high correlations. The general pattern of the observed teleconnection in the top left is representative. We have this kind of warming over Alaska and Canada when we have an El Nino event. But you can see kind of the details of that warming spatially are a little bit different between models and a little bit different between models and observations. If we look at the same member for rainfall or precipitation in the bottom, we get a similar kind of answer. That general pattern of the teleconnection is there, but there are kind of little spatial differences, which we might expect because these are global coupled climate models. They run on kind of a 1 or a 2 degree grid cell, so they're kind of quite coarse. We can do the same thing, but flip it around and now look at the highest correlated member for precipitation. And we see that this improves the precipitation pattern a little bit. It looks more like observations, and we still get pretty high correlations. And then if we look at the same member for temperature in the bottom, you see it kind of degrades. It degrades the teleconnection just a little bit, but we still get that overall pattern. And so I think what we can really conclude from this is that the models are able to represent the overall pattern of ENSO teleconnections, but we want to be a little bit careful with the details, particularly if we look at the details of somewhere kind of on the edge of the large anomalies, we might see differences between the model and the hogs. And we can do the same thing for the PDO pattern to see whether the models can actually get a PDO. Again, this is a very similar plot. We have observations in the top left and then all of the models. And we get pretty high correlations actually in all ensemble members for the PDO. And we get a pretty good PDO pattern. There are small differences between the observations and the models, but we do see the largest differences kind of in the regions we're less interested in on the kind of western side of the North Pacific. So that's kind of promising. We see really similar observations and model results kind of off the coast of North America. So I think from these plots we can say we can use the models to look at our scientific question, but we want to be a little bit careful with looking at individual locations and details of the patterns that we're interested in. Okay, so now I'm going to take my models and I'm going to composite events and see how different impacts, how different the impacts of El Niños are when the PDO is in different phases. And so here what I can do is take all El Niños when the PDO is positive, and I get the map shown below. I can then do all El Niños when the PDO is negative, and I get this map here. And here I'll note that stippling is when the two maps are not statistically different. So no stippling means they're different, stippling means they're not. And I know people have different ways of deciding whether they stipple the statistically significant or the non-statistically significant parts. And here you can see the statistically significant different part is really Canada and Alaska, where we get these strong warm anomalies when the PDO is positive that aren't there for El Niños when the PDO is negative. We can do the same for rainfall. And here we see the biggest difference in this blob off the California coastline that is much stronger when El Niños occur during a positive PDO than a negative PDO. Okay, but I told you I was going to look at multiple models because our models do okay at representing the teleconnections, but they're all a little bit different and none of them are perfect. So we're going to extend this down and look at all of the smiles I have. Okay, and so the top row is exactly the same, but now I've added all of the models. And actually we get a really consistent result. We find the same regions of difference in all the models. The patterns are a little bit different, the magnitudes are a little bit different, but we really do find in all of our models that when we have an El Nino and a positive PDO, we have these anomalies over Alaska and Canada that are much stronger, and these rainfall anomalies over the Californian coastline that are much stronger compared to when the PDO is negative. Yes.
Sorry, I think I misheard what you said. The stippling indicates
Not statistically
so
different.
like for the El Nino PDO plus, where it's stippled, that pattern is no different than you would get from just this plain old El Nino.
So that means that this and this are not different. So we're comparing these two.
Got it.
And when it's stippled,
I see.
they're statistically the same, and when it's not stippled, they're statistically different.
I see. Thank you.
And that's just because Jen likes to stipple things that are not statistically different. She thinks if you put it over the statistical interesting stuff, then you're wiping it out.
Okay.
Which I think is a good argument. Okay.
I'm just trying to figure out what to focus on.
Yeah, so focus on where there's no stippling.
Thank you.
Okay. Okay, and so we find this result that is much more consistent across models than I thought it was going to be, which is kind of cool. And so we kind of then wanted to delve into what's going on. When we have an El Nino and a positive PDO, does the PDO enhance El Nino? We know that they both impact North America. Do they just kind of add together to see what we're finding? What's going on? And because we have the large ensembles, we can really start to, disentangle the effects. So what I can now do is I can take these plots again and I can take El Niños when the PDO is neutral, because I have quite a lot of these years across the large ensemble. I can then take PDO positive events when ENSO is neutral. So now we just have the effect of El Nino, the effect of a positive PDO. We can add them together And then we can say, well, does that plot on the right look the same as if we have a co-occurring El Nino and a positive PDO? And actually it does. They look really similar, and I don't have significance on this plot, but I did make one with significance, and they're pretty much the same. And again, we can extend that down to all our models, and we find a pretty consistent result. That really what we're seeing here is two modes of variability. They both affect North America. They don't really seem to be interacting in this region a lot. They just kind of add together to give us our impacts. And we can do the same for precipitation, and we kind of find the same result. Or we do find the same result. Okay, and so we found these results, and what we really wanted to know then was kind of to look at the circulation and try to understand what happens over North America when we have an El Nino and a PDO event. And to do that, I'm now going to just focus on one model, this GFDL sphere med model. And I'm going to do that for a couple of reasons. First, this model is the highest resolution, and you can kind of see that there, how it's got better spatial detail than the others. It's 100 kilometers over the land and the atmosphere, so it's much higher resolution than the other models. When we compare it to observations, it consistently has the highest correlations for everything we look at in this region. And I'm not going to show you all of the models just because you can already see a lot of plots. It's going to get way too crazy. So we're just going to focus on this one. Okay. And so I'm going to start by showing you things I've already shown you, and then we're going to add some atmospheric circulation fields. So here we have temperature again when the PDO is neutral, and El Ninos are happening. So this is kind of the typical impact of an El Nino on North America for temperature. And then I can show you those same plots again, El Nino when the PDO is positive, El Nino when the PDO is negative, and the difference. Okay. We can add precipitation, again the same plot, so we're still highlighting the same areas, that Alaska and Canada signal and that California coastline signal. But now we can add more variables. So now we're going to add sea level pressure. And so here you can see this giant pink blob. This is the Aleutian low, which we know occurs during El Nino and PDO events, and is responsible for some of the atmospheric circulation going on. So here on the left, you can see this Aleutian low that's occurring when kind of the strong Aleutian low during an El Nino event. And what we find if we go to the right is that Aleutian low is enhanced when the PDO is positive, and kind of degraded or weakened when the PDO is negative. And you can see the difference on the far right. And this should explain quite a lot of those temperature anomalies, because when we have a stronger Aleutian low, we have more warm air from the tropics getting up into Alaska and Canada, and this could really be responsible for the temperature pattern we see in the top. The other thing we can look at is the zonal mean, zonal wind, which is basically the jet going kind of across the Pacific and onto the North American continent. You can see that here in the black is the mean. And so we know when we have an El Nino, that jet is strengthened and moved equatorward. And you can see that in the red. And we kind of find the same effect here. When the PDO is positive, this jet anomaly is enhanced. When it's negative, the jet anomaly is diminished. And this can account for some of those precipitation changes we see when we have a stronger jet. We're getting kind of more rainfall brought onto the coastline. Okay. All right. So the last thing I wanted to do here is think about this in terms of probabilities, because I have so many events out of the large ensembles, I can start to look at distributions rather than kind of two patterns, because what goes into those patterns are a lot of events that maybe are not exactly the same. And so here, what I'm showing you is Alaska. We've now just averaged over the Alaskan region. And these are temperature anomalies. So you can see in neutral years, so nothing's going on with ENSO and the PDO, we have this kind of distribution. Some years are warm, some years are cold, it's centered on 0. This is something we might expect. We can then look at El Nino years. And so you can see when you have an El Nino, that distribution is shifted to the right. So we have a warmer mean, we have warmer anomalies, but we still could have a cold year when we have an El Nino, because it's not the only thing going on in Alaska, and it's not the only thing that's important. We can do this again for El Ninos when the PDO is positive, and you can see that shifts the distribution right a little bit more. Same answer, we could still have cold anomalies, but we're more likely to have warm anomalies, and the tails of the distribution are kind of shifted more into the warm region. And when we have a PDO negative, it shifts back, that's the green, starting to kind of layer on top of each other. So you can kind of see what we're really seeing in this study is not huge impacts of these modes of variability, but we're seeing a shift in a distribution. We can expand this out to other regions. I'm not going to go into this into too much detail. The bottom left is offshore of the western US coastline. This is where marine heat waves occur. We find the same kind of distribution shifts. Interestingly, for rainfall on the right two panels, we actually don't find any significant distribution shifts for the winter season over the Colorado River Basin or in San Diego, which is kind of in the middle of that California blob that we were looking at. But if we then move these plots exactly the same, but this is now March, April, May, we do find significant differences in those rainfall regions. And this is something that would be interesting to look into further, kind of the seasonal dependence of these differences, and maybe the rainfall changes are more important in March, April, May than they are in DJF. Yes?
Is this a time-lagged precipitation where you have ENSO earlier and the rainfall later?
Yeah, so it's exactly the same data, it's just looking at the impact in March, April, May instead of December, January, February.
Okay.
I hesitate to say summer and winter because I've lived in too many hemispheres and I get really confused. Okay. Okay, so to answer the first scientific question of this talk, what have I found? I've found that the PDO modulates ENSO teleconnections over North America. So basically when you have an El Nino and a positive PDO, you get these larger temperature impacts over Alaska and Canada and this larger rainfall over the Californian coastline. And that's driven by these atmospheric circulation changes in the Aleutian Low and the Pacific Jet. We found that this effect is just really an addition of the impacts of the two different modes. They're not really interacting with each other, they're just kind of, they both have effects and they add together over this region. And I think really importantly, we've found that these modes of variability are useful for kind of policy, for understanding distribution shifts and the likelihood of having temperature and precipitation anomalies in different parts of the US. But they're not deterministic predictors. So if we know we have an El Nino and we know we have a positive PDO, we do not know that it's going to be warm over Alaska. We know it's more likely to be warm, but it's not 100% going to happen. And I think that's a really important point to emphasize because we can get a little bit wrapped up in trying to use things as predictors when they're helpful, but they don't tell us the whole story about everything that's going on in the US. Yes?
With your distributions that you were showing there, is it really just a simple shift one direction or another, or is there a change in skewness?
Yeah, that would be worth looking at. And I think that for the purposes of this talk and this study, we've kind of just fitted a Gaussian, but that may not be the best fit, and it might be better to fit a different sort of distribution and look at the differences. I hesitate to look at the skewness because we have a lot of events from these large ensembles, but I'm not sure if we really have enough events to really get the perfect distribution, if that makes sense. So,
Because it looked like it was Gaussian on your diagrams, but I didn't know if that was just idealized or...
yeah, so I mean, the histogram behind it is the actual data, and then the curve is the fit, and I do that because I know the Gaussian fit. It looks nice, but it's maybe not telling us the whole story, and so rather than just show you the kind of fit, I like to put the actual data behind it, if that makes sense. It does look kind of Gaussian, but yeah, you can kind of see, like, even just here, we're not really capturing the entirety of the distribution because I think we need bigger ensembles, and that would be a difficult thing to do. Does that answer your question?
Oh yeah, thanks.
Okay. Cool. Okay. And I'm happy to answer questions about this, or you can check out the paper that's now been published, which is... Okay. And so I'm going to use the rest of the talk to talk a little bit about ENSO projections. So I'm going to shift gear a little bit and stop talking about ENSO and its impacts on North America and start talking about, does ENSO itself change in the future? And this is kind of an important question because it has impacts all over the place. And so we want to know if in 100 years we're going to have stronger El Niños, because then we might have stronger impacts in different parts of the world. Okay. And so people started looking at this quite a long time ago, and this is one of the nice plots that came out of CMIP 3, so 2 IPCC reports ago. And here you can see a bunch of models in different symbols, and kind of a future projection of the change in ENSO variability on the y-axis and the change in the mean state of the Pacific in the x-axis. So if we move up, ENSO variability increases, and if we move right, the Pacific becomes more El Nino-like, which basically means the east warms more than the west. And you can see more models show an increase in ENSO variability and an El Nino-like warming than don't, but not every model shows the same thing. And this was kind of the state of the knowledge in CMIP 3. If we jump to today, we now have CMIP 6, and we have different experiments that can help us to tell us what's going on. And the top panel here shows kind of the results from CMIP 6, which show the future, or 2000 to 2099 in orange, and the past, 1900 to 1999 in blue, in all of our CMIP 6 models. And this is looking at a change in one of the metrics for ENSO variability. And here you can see all of the models show an increase in ENSO variability when you take these 200-year periods. However, if we look further into the future and look at equilibrated experiments on the bottom, so these are now experiments with increased CO2 that have been run out to equilibrium, we see that in most models ENSO variability decreases. And so this kind of brings up some really interesting questions about the transient or the temporal changes in ENSO variability. We're seeing, if we take long averages in the transient kind of near future simulation, ENSO increases, but if we look way out into the future, ENSO decreases. And so what we want to do is, or what I'm going to do, is take a whole lot of smiles and look at the temporal evolution of ENSO variability in the future to kind of see how it changes over time. And I can do this because I have so many ensemble members to average over. Okay, I think I pretty much say that in this slide. And so today I now have not just 5 smiles, but 14 from CMIP 5 and CMIP 6. And if anybody's interested in using these, we're regridding them all onto a common grid. So you should shoot me an email or ask me if you're interested in using the data, because it's now easier to use because it's kind of all consistent. And so what I'm going to do is look at the future of ENSO variability. And today I'm going to take just a simple ENSO variability metric. And so to quantify ENSO SST variability, what people typically do is they take a box in the Pacific and they take a standard deviation over the box, and they call that ENSO variability. And there are more fancy ways to look at this, and there are lots of different boxes you can look at that quantify different parts of the Pacific. And today I'm going to focus in that giant blue box in the middle, which is kind of your standard Nino 3.4 region, which captures kind of, I guess, a large chunk of that ENSO pattern that you can see underneath it. Yeah, if anybody wants to talk afterwards about other cool ways to quantify ENSO, I'm happy to do that, but we're going to start with the really simple definition today. Okay, so here are our 14 models with observations on the bottom right. Nino 3.4 is the black line, and then 2 other boxes are shown in blue and red, but they all kind of do the same thing, so it doesn't really matter. We have 3 lines for each color, which basically just show the mean of the smile and the spread of the smile, but again, they all kind of evolve the same way, so what we really want to look at is the evolution. And by first glance, looking at this, you can think, okay, the models aren't doing the same thing. We can start by looking at individual models. So this is the access model on the top left. You can see in the historical period, ENSO doesn't change much, and then in the future, it goes up. we can look at one of the GFDL models on the right. You can see ENSO increases in the kind of historical period and then decreases in the future. You can look at one of the Canadian models, and I'll note this doesn't have kind of the beginning of the time series because they ran their model from a later start date, but it shows a pretty solid decrease. We can look at this IPSL model, which shows kind of a linear increase over time. We can look at the MPI model that shows no change in ENSO at all. So what you can really see here is a whole lot of different things going on at different times in different models. Okay, so what about the pattern? What does the pattern of change look like? So here I'm showing the tropical Pacific, and I'm showing the pattern change in 2021 to 2050 compared to 1951 to 1980. And what I really want to note here is that bottom right panel is the multi-ensemble mean. And it looks really, really like the CMIP multi-model mean. We see this kind of weak increase in ENSO variability, but centered on the Central Pacific. People have shown this before. However, when we tease out what goes into that mean in all of the different plots, you can see the patterns are really different. And what we're really doing is averaging out a lot of the model differences by taking a multi-model mean. And so I'm showing this slide to kind of feel a bit beware of the dangers of doing so for something like ENSO, where the models are doing really different things, and when we average them together, we're losing a lot of those model differences. We can look at a later period, so the end of the century, 2070 to 2099, compared to the same base period, and we get a similar but stronger multi-model mean pattern on the bottom right. And again, we can see what's going into it is really different. I'll note that a lot of these models have kind of a similar but stronger pattern. If you look at those two plots next to each other, you get kind of the same pattern but stronger in the later period compared to the earlier period. But not all of them do. So look at the top right. This is the CSM model out of NCAR. And if we look, I'm going to flip back and forth between the earlier and the later period. The earlier period looks like this. The later period looks like this. And so they don't have the same pattern change in different times. Just let me finish the sentence. So basically that tells us it's not only important to look at the different models, but to look at different times, because there is some sort of temporal difference between what's going on in some of the models. Yes?
This is variance, 2 to 7 year bandpass variance. Okay.
Sorry, I should have said that. Yeah, it's variance. Yeah.
Just a quick question. Does this single image have multiple ensemble numbers as well?
Yep.
This is a mean?
This is a mean across all the ensemble members.
Have you, I can ask the later question later.
Okay. Cool. So what we're really trying to pull out is the mean change of ENSO, I guess, to get at that point, the force change in ENSO. Okay. And so we've looked at this in a whole bunch of different ways, which is kind of what I'm showing you here. Here I'm now showing that same Nino 3.4 box and looking at the standard deviation change at different seasons. So this is the ENSO variability change in different seasons, and this is the end of the century, so 2071 to 2100. Each model is shown in a thin line, and the multi-model mean is shown in the black line. And here we actually find some model consistency. We find a lot of the models show an increase in the variance that's really centered on the kind of August to March period. You can kind of see those in the pink. The pink is increase, blue is decrease. And a decrease in a lot of the models between March and June. And so that's kind of an interesting result, because that tells us when ENSO peaks. So ENSO is strongest in Northern Hemisphere winter, so kind of October to February. That we're getting most of the increase in variance when it occurs in those seasons. And so not only are we seeing model differences and time differences, we're also seeing seasonal differences. So this is getting kind of complicated quite fast, but it's kind of really interesting to see that we don't just want to look at ENSO's peak season, we want to kind of pull out the months individually and see what's going on. Okay. So the other thing that I'm going to remember back to that CMIP 3 figure I showed you. where we talked about the mean state warming in the Pacific. And so people have talked about how the mean state warming of the Pacific might be linked to ENSO changes. So to understand how ENSO changes, maybe we want to know how the Pacific is changing over global warming in its mean. And so here I'm showing you those models again with the multi-model mean or multi-ensemble mean on the bottom right. And here I'm showing a metric for the mean state change in terms of the East and the West Pacific. So basically what we're looking at is, does the East Pacific warm more than the West Pacific? So here white doesn't mean no warming, it means the whole Pacific is warming at the same rate. Red means that the East is warming more than the West. So if we think about the Pacific, the East is warming more than the West. And blue means the West is warming more than the East. And this is kind of important because where it's red, the East is warming more than the West, and this is a similar pattern to El Nino itself. So this is kind of El Nino-like warming. Whereas when the West is warming more than the East, that's La Nina-like warming. Okay. And again, I'm showing you a seasonal dependence of this warming. So if we look at the bottom right, that multi-ensemble mean, we can see all of the models show an El Nino-like warming in all seasons if you average them together. And that's again pretty consistent with our CMIP results. However, if we tease the models apart, we do still find that most of the models show this El Nino-like warming in red, but depending on which model you look at depends on which season that warming is strongest in. And some of the models do show La Nina-like warming, and some of them, it depends which season you look at, how the Pacific is warming. And so there's a lot going on here that is a little bit more complicated than the models will show El Nino-like warming in all seasons, which is something that has, I guess we maybe would think from that multi-ensemble mean on the bottom right. Okay, so I've shown you a lot of things here, and I'm just going to show one more figure that tries to kind of bring this mean state change and the ENSO change together. Okay, so here we have 4 quadrants, just because if you plot all 4 quadrants on top of each other, you can't see anything. We're now looking at time in color, so we're going to follow the evolution of the dots, which are the ensemble means, from blue to yellow. The y-axis is ENSO variability change, so if the blue to yellow goes up, ENSO variability is increasing. And the the x-axis, so this one, is the mean state change. So if we move to the right, it's that El Nino-like warming, so the East warms more than the West, and if we go left, it's La Nina-like warming. And then all the little dots are just the first and the last time point, so you can kind of see the ensemble members around the mean to see what the spread's really like. Okay. So at first glance, this looks really hard to interpret and like a bit of a mess. But when we start to look at the models individually, we start to see some consistency in their evolution. And so I'm going to stand in front of the screen and point out one of the models. So here's CESM1. So here we can see we have an increase in ENSO variability that kind of plateaus. We then have an El Nino-like warming. If we look at other models, we start to see a consistent pattern. This one, increase in ENSO variability, El Nino-like warming. Increase in ENSO variability, El Nino-like warming, decrease in ENSO variability. Same for this model, increase, El Nino-like warming, decrease. And so not all of the models are behaving this way, but a lot of them are. And a lot of them are showing part of this kind of hook-like pattern. So we think that this is starting to maybe bring together some of those differences, and maybe what we're seeing between the models is that we shouldn't really be looking at how they evolve at individual time points, but how they kind of evolve in this space over time. And this kind of brings together that plot I showed you way back at the beginning of this section, where I said in the transient sense, previous studies have shown that ENSO increases in variability, but in the long term it decreases. And so this starts to link some of those studies together. The other thing I'll just briefly note here is those little dots. And you can see the spread of the ensemble members is really large in ENSO variability space and less large in the mean state space. And that just tells us we really need these smiles to get at ENSO variability because the spread is large, but we don't need as many ensemble members to look at the mean state change. Okay. So, what have I shown you? I've shown you that ENSO variability projections are time dependent. The pattern is different between different models, but there does seem to be some kind of consistent increase in seasonality, where the increase in ENSO variability is in this kind of DJF peak season across the models. The mean state of the tropical Pacific in the ensemble mean shows an El Nino-like warming, but there are differences between models in which season this happens, and actually some models show the opposite response. And I finished by showing you these kind of hook-shaped time evolution patterns, where we see this in many models. There's an increase in ENSO variability, then this mean state change, and then a decrease in ENSO variability. And that's kind of really interesting because that tells us that the ENSO changes are preceding the mean state changes, not the other way around. So we're not seeing a mean state change that drives the ENSO change, we're seeing an ENSO change that precedes the mean state change. And I think that starts to link together these previous studies we've seen before. And so I'd just like to finish by summarizing kind of the two parts of my talk and kind of emphasizing that these smiles are an amazing tool to look at climate. They're really useful to look at rare events or combination of events, and I've shown you that for the PDO and ENSO in the first part of the talk, but you could also use them to look at things like extreme events that are, or probability distributions that are hard to sample with traditional CMIP climate modeling. The smiles can also tell us something about the time evolution of quantities like ENSO that are inherently variable. And here I've shown you that we do find a lot of model differences between the smiles that we can quantify because we have them. And hopefully try to convince you that there's some consistency if we start to look at things in new ways, like looking at the ENSO variability and the mean state changes and their time evolution in these books. And I'm happy to take questions, and you can check out this work in the publication and the preprint. Thanks.
There was some questions. If anyone has questions.
Yeah, I have one about these sort of phase-based diagrams, really interesting with the time coloring. Do you think that the changes in the basic state feeds back at all into the variability, and that if you decrease the basic state, then a given El Nino year can't be as a large magnitude?
Yes, I do think that the mean state does affect El Nino. I just think it's really interesting that we first see El Nino changes, and then we see mean state changes, and then we see the decrease. So I wonder if that's kind of linked in some way. It'd be cool to look at it in more detail. But I definitely don't think the two are completely independent because, I mean, everything in the climate system is linked, and if you change kind of the temperatures, you change the circulation, and then you have to change it, so.
I guess following up on that, so in those diagrams, when you're saying mean state, you're referring to the like more La Nina-like versus more El Nino-like mean state. So would you still expect the variance to change with a general warming? So even if it's not more on one side of the Pacific or the other, during that period of general warming, you would still see increased variance just because, like, over the last 30 years, like, El Nino in a warmer climate state will look like it has more variance.
I would expect to see differences, but then we have this MPI model where the mean state, like the whole tropical Pacific is warming and ENSO isn't changing.
Mm-hmm.
And so I think that tells us that we don't really understand ENSO dynamics, and we definitely have issues modeling ENSO dynamics. So I guess the answer is that would be something, looking into why in more detail is something I'd like to do. When we did this, we only had sea surface temperature, so that's kind of, we wanted to see what the models were doing, but we couldn't say anything about why. Now we're starting to put together an archive of more dynamical variables. I don't think we can look at 14 models and say why each one individually does something, but we could potentially pick 3 interesting models that do different things and try and understand why and how the mean state of the Pacific and the Enso variability changes are linked together. So I guess I'm not giving you any answers, but saying I think there's a lot to be done in this space and still huge open questions, because given our models do different things, that tells us we don't yet understand how to model the system properly.
It's very interesting to know that you can add a PDO and ENSO pattern linearly. So is there any linear change between ENSO change and temperature change over North America, or precipitation change?
Yeah. So I'd just like to first premise that with you can add them linearly over the specific region I looked at. That is probably not true in the entirety of the globe. In terms of looking at the future, we've started to look just a tiny bit into projections, and we're finding a lot of model disagreement again. So I don't think you can just link them together, but maybe some of that model disagreement can be understood by the disagreement in the ENSO change itself. So Dylan Maher in NOAA is looking at some of these questions for ENSO predictability and starting to find things like the models that have a decrease in ENSO variability show a decrease in predictability in the future, and those that show an increase show an increase in predictability. So that's probably not quite the same question, but yeah, I think there's kind of, I feel like a lot of my answers today are going to be really interesting, hard to disentangle, and we don't know. I'm very sorry about that.
I think in general, that seems like a fair statement about ENSO changes as well, though, so that's good. That's a good problem. Pete, you want to?
It's a question online from Liz Maroon. First of all, she says, great talk. She says, ENSO and PDO are likely not independent modes of variability. The two interact. Do you see different frequencies for composite categories? For example, more ENSO positive with PDO positive than ENSO positive with PDO negative?
We do. So the two are definitely not independent. And I think we can say that from what we're looking at, a lot of their impacts can be linearly additive, but certainly ENSO and the PDO themselves are not independent modes of variability. And you can definitely see that in numbers of events. You have more El Niños and positive PDOs and La Niñas and negative PDOs than the others, and we see that in both the models and observations. And so I think there are really interesting questions in trying to disentangle the impact of the modes on each other. In terms of this study, what we really wanted to say is if you know the two, and you don't care how they interact, you just want to know what that means for where you live, what can we say? And so I think those are two kind of different questions that you would address in very different ways.
So mine is actually directly related to that.
Yeah.
So that's part one of my question, but I guess the second part of this, and it's more of a comment, since that was the question, with regards to the fact that PDO and ENSO are so closely linked, my mind went to the Newman et al. 2016 paper, which decomposed the PDO into different components. And one was the Eastern Pacific ENSO, and the other one was Central Pacific ENSO, and then the Pacific Decadal variability, that kind of that separating subtropical component. And I was wondering if you may be able to better separate these if you, like, say, focused on, instead of PDO, if you did, say, just focus on that Pacific decadal variability in subtropics, that's separating subtropical mode, and say just look at this with positive ENSO and negative. It's something that's kind of more separate if we get cleaner separation between those.
Yeah, you potentially could. I think there are also questions around, I'm saying PDO drives the elution low, drives the impacts, but actually the elution low and the PDO are also kind of in this little loop, so nothing is completely independent. And I think you're right that it would be cool to try and disentangle it in maybe that atmospheric component, or, even to run experiments where you were able to just kind of impose part of the variability, if you could separate it and see how that, what impacts that had. Yeah, that would be cool.
Yeah, can your combination PDO ENSO analysis shed light on why it's been such a strange La Nina year in terms of rainfall in California? Because you'd think it would be drier, but it sure hasn't played out that way.
Somebody asked me this like a year ago, and I think we looked and we found that no, it can't. We're in the wrong phases for this to be very helpful at all. But we were talking, I think I was talking to someone yesterday about this, about the idea of, because we have so many events here as well, if you could pull out triple La Ninas and see how they differ from, I'm sure I was talking to one of you about this, and I talked to too many people, about pulling out, yeah, you can't do that in observations because we have, what, 2 or 3 observed events. But if we get models that can do that, and I know the CSM1 model can get these multi-year La Ninas, whether you could pull them out and see if they look different to just single-year La Ninas, and whether that would maybe tell us something interesting. I haven't done that, but it would be cool, and happy to provide the data if somebody does want to go in that path.
All right. Thank you very much. Let's thank Nicola one more time. And so Nicola is going to be heading to the airport very soon, but there is pizza in the whatever that 853. Yeah, so we can all head over there if you'd like, and we can continue conversation there as well. So.